So in signals, so we call a concept called as linear convolution. So we know that we can construct a filter in analog using op amp. We call it as low pass filter, high pass filter and band pass filter, like that. Similarly, in a digital format also we can construct a filter. So the basic filtering process of a signal, it starts with a linear convolution. So convolution is a process. When we do convolution, some signals will be filtered out, and this is the basics of a digital filtering technique. So now within a short time I will try to cover what is this linear convolution and how this process can be done, and we will see one example also. So basically we define linear convolution in two domains, that is one in continuous time domain, continuous time. So we call it as y of t is equal to x of t convolution with h of t. So this is nothing but integral minus infinity to infinity x of tau into h of t minus tau. So this is what we do. So in the previous class they have explained that when you want to take the linear convolution, so both the signals should have some area under that. Area under that curve will give the convolution. So for doing this we require two basic process of signals, that is shifting and folding. These are the fundamental process we have to do when we do convolution. Similarly, in discrete domain also, so we can do convolution. It is called as y of n is equal to x of n convolution with h of n. So that is nothing but summation. So k equals minus infinity to infinity x of k into h of n minus k. So this is what the convolution process. So now as it is very easy to do in discrete domain, so let me take an example and explain how this convolution process will take place. So before that let us learn what is meant by shifting of a signal and folding of a signal, because very important when we do this process convolution. Suppose let us take a signal. So I have a signal like this. So this is 1 0, sorry, minus 1 1. See, I want to shift this signal. Shifting is a basic process. So let us take like this, x of t minus t naught, x of t minus t naught. So we can do shifting either right side or left side. So if t is greater than 1, we call it as t is greater than 1. So we have to shift the signal in the right side. If it is less than 1, we have to shift the signal in the left side. Suppose if I take like this, x of t minus 1. So x of t minus 1, so we are shifting the signal in the right hand side. So then it becomes minus 1, this signal will come to 0 and it will come like this. So this is what is the shifting process. So this is 1 and this will become 2. This is what right shifting. Similarly, we can do left shifting also. It will be t plus 1. If I shift this one, this will move to minus 1 and this will go to minus 2. So these things are very important for the linear convolution process. If I do left shifting, this will be x of t remains same. So this will become minus 1, this will become minus 2. So this is what the signal we get. This is called as the signal shifting towards left side. So there is a concept called as a folding of a signal. So it is called as x of t is equal to, if I do minus of x of minus t, we call that process as folding. So if I have a signal like this, if I have a signal varying from 0 to 1, so if I want to fold this signal, so this is on the right hand side, it has plus. So if I fold this signal, so I will get the folded signal like this. So actually we can call this as the mirror image of this signal. So these two operations are very important in convolution process. So convolution is the basic thing we do in digital signal processing. So for any digital signal processor, if you want to do filtering process, it will do convolution only. Okay, so let us take a simple example. Okay, so these are two signals given in discrete domain. So let us see how to do convolution process. As the formula says, this is summation n is equal to, sorry, k is equal to minus infinity to infinity x of k into h of n minus k. So here, as you are seeing, there are two operations are being taken place. One is we have to shift the signal, second one you have to multiply, and then you have to do summation. So three operations are involved in this process. So that's why, so in all the transformation we prefer frequency domain, because in frequency domain it is only the multiplication of two signals. So here we have to do three process. One we have to do shifting, then multiplication, then summation. So three processes are there, therefore it becomes laborious. So therefore we go for frequency domain process where we multiply the two signals. Now let us see here how to do this. So I'll keep x of n constant. I'll try to shift this h of n. Okay. So I will take the first sample, so which is 0. So this is 1. So then I'll take h, I will put k is equal to 0 here. So let us see. So it is 0 to 3. I'll put now in this formula 0 to 3, because we have got only the 3 samples here. So there is no minus part here. So that's why I have reduced it to 0 to 3. Let us put 0 here. It becomes, so x of 0 into h of n only. So therefore I will keep the sequence like that only. So this is 0, 1. So it is in 1 it is 0.5, and in 2 it is 0.25. So let us multiply this. So I'll call this as x1 of n. So I'll multiply this, or I will output this is y1 of n. If I multiply, so I will get it as 1, 0.5 and 0.25. So this is what the output we get. So I'll call this one as the first output. Then I'll take the second one. So this is 0. I'll take 1 here. So in 1 there is 1. Now what we have to do is we have to shift, because this becomes 1 here, x of 1. This will become h of n minus 1. That means we have to shift the signal by 1 unit. So therefore I'll shift the signal here. So I'll write 0 here. So now in 1 I'll write it as 1. In 2 I'll write it as this is 1. In 2 I'll write it as 0.5. In 3 I'll write it as 0.25. Now let us try to multiply this one. So again I will get 1, 0.5 and 0.25 only, because we are multiplying it 1. So therefore I will call it as y2 of n. So it should be shifted. So I'll write like this. So this is 1, this is 0.25, sorry 0.5 and 0.25. So this is what the process is. Next I will take the next sample. So this is 0, 1, and I will take 2. So this is 0.5. So now again we will shift 1 unit. So this is 0, 1. So this will be 2. In 2 this will become 1. So in 3 it will become 0.5, and in 4 it will become 0.25. So now let us multiply here. So this will be y3 of n. So I have to leave 1, 2 space here and then multiply here. So this will become 0.5 and then I think 0.25. and then I think if you multiply 0.5 and 0.25, that is 0.125. So this is how we carry out the process. And last one, so we have, so 3, yeah. I think I can shift that, yeah. So let me write, so this is 3, this 0.2, 0.5 only, so 0, 1, 2, 3, I think. So now I have to write in, I think 3, right? So this is 1, so this is 0.5 and this is 0.25. So now again if you multiply you will get the same output only, 1, 2, 3 I will leave, and then I will put 0.5, 0.25 and 0.125. So this is what the final output y3 of n. So if you add all these, that becomes the convolution sum. If you add this, this is the convolution sum. Let us try to add this. So I will put 0, 1, 2, 3, 4, 5. So first one is in 1, 0.5 and 0.25, and second one is in 1, 0.5 and 0.25. Third one is in, so this is 0.5, 0.25 and 0.125. Fourth one is in 0.5, 0.25 and 0.125. So we will try to add this one. So this will be 1. So this is 1.5, 0.5, 0.5, 1, 1.25. So this is 0.5, again 1, and this is I think 0.375, no, 375, and last one is 0.125. So this is what the convolution. So as the samples are on the right hand side, this we can call it as a causal sequence. So therefore I can put the arrow mark here. So it is on the right hand side. So this is what the convolution process. So this is very important in signal processing. Okay, all the processors they use this technique in doing the signal processing. So I think all the transforms have been dealt with. Another small this one, there is another transform called as DFT. It is called as discrete Fourier transform. It is been derived from DTFT only. So in DTFT we are not worried about the periodic property of the sequence. So for aperiodic also we can apply DTFT property and we can get the output. Whereas in DFT it says that it should be, the signal should be periodic, and then only we can take the discrete Fourier transform. So it is defined like this: x of k is equal to summation, so n is equal to 0 to, so it is n minus 1 x of n into w n of k of n. So this is what the basic definition of discrete Fourier transform. As you are seeing that it is defined for a known length, where n represents the length. So this is extensively used for taking the fast Fourier transform, FFT. So I think all the softwares they do this process only. In MATLAB if you put FFT, it does with this equation only. This is called a basic synthesis equation. So where this W of n is called as the twiddle factor, it is nothing but e to the power of minus j 2 pi by n. So the samples are sampled at an interval of 2 pi by n, n represents the number of samples. So the easiest way of carrying out the discrete Fourier transform is, we can knowing the number of samples, we can reduce it to a matrix form, where we can write like this: if I take n is equal to 4, if I take n is equal to 4, which is a 4 sampled DFT, I can write in the left hand side x of 0, x of 1, x of 2 and x of 3 is equal to 4 by 4 matrix of the twiddle factor and so this is nothing but small x of 0, small x of 1, small x of 2 and small x of 3. So, this is a simple process of taking the discrete Fourier transform in matrix form. So, this is one of the transform that we use in signal processing. Thank you. Now, in all institutes we are using MATLAB. In some institutes we may have licensed versions or some we may not have licensed version. So, therefore, there is another software which is called as Octave, which is a 7.3 version. It is available. So, we can use this Octave software to carrying out all these signal processing activities. It is for UG students. So, it is available both in the Linux version and Windows version. You can install that. It is a freeware software. So, online also it is available, sir. That is the beauty of this software. You can give assignments, lab assignments to students and you can ask them to submit online also. They can use that. Yeah. Nyquist plot and all, it is quite difficult because for that you have to download library, you have to go to GitHub and then you have to download that, then you can work. So, root locus you can do, okay, and then polar plot you can do, and then all control systems toolbox is available and signal processing toolbox is also available. So, this is a freeware software which all of us can use. Okay, thank you very much.
I will take simulation at the end. Before that, all of the TAs have the graded assignments which they want to discuss with all of you. A comparative study between the what you did last week and what were the answers last day, right? Okay.
Initially, it was observed like some of the guys were like very well versed with the subject segments. For others, it was like they had a common plan to teach the subject for any engineering course. They were having a common plan to teach the subject. They were not specific to signals and systems, but afterwards, it was observed like the approach was more towards teaching signals and systems.
Yeah, so significant improvement has been there. So before the regarding the pre-course assessment, the average grade of the class, we did in fact assign grades to both your pre-course and post-course papers. The average grade before the course was 6.04, I think. Yes, we assigned 5 grades arbitrarily: 4, 6, 7, 8 and 10. And after the course, we're very happy to see that it is now 6.94. Right? So we should all clap for ourselves. It's a very good improvement. And yeah, we are able to see quite a bit of improvements in your course structures in the majority of your papers. So yeah, I mean, if you'd like to say anything.
Yeah. Additionally, the 10 grade criteria was basically courses which we would love to take if there was something innovative in them. So before this course started, the first assessment, we had maybe 1 or 2 papers which we graded 10. Afterwards, we got at least 8 to 9 papers which we graded 10. That's a great improvement.
And some of the course plans, like in the beginning, almost, I mean, the majority of the class did not mention some contents like the sampling and reconstruction thing, but afterwards we saw that everyone was at least clear with all the contents and how to plan that. And the planning was also initially generic, like we'll take lectures, practicals, but after that, after sir's teaching, there was specific ways of teaching, which was think per share and everything. So I'm happy that you guys are at least understanding the student's perspective.
You will not be privy, however, to see your own code. We will keep those for now. We will not be able to see.
Thanks, sir. What's that for their own purpose?
I will keep the simulation part into two halves. One is Python and one is JNE radio. How many of you are well aware of Python? Like, okay, okay, ठीक है. I will share the codes, everything, but हाँ, it like आप सबका focus was कि in your course assignment was कि towards giving a mini project or mini assignment in the form of coding, and in this age of 2025, everyone is shifting to that area. So I believed कि we can have such an assignment which you can also share. So this is one Python notebook. Like सब कुछ ready करके रखा हुआ है मैंने इसमें कि कुछ code करने की जरूरत नहीं है. So I will just demonstrate. Like here are the basics. Like basics of signal processing, which you all taught in peer learning also, and sir also did. Basics, how the analog did happen. Sampling and quantization, which sir did today only. Okay. So what I have started with, I have started with a very basic signal, which was 0.85 to the power t square. Right. For a continuous signal, I am doing sampling as well as quantization. As you can see, sampling code and quantization code. How it will look like this. If this is the basic signal, which is 0.85 power t, if we sample for nth intervals, we are getting these points. And I hope you all know what quantization is. So if sampling is basically taking points from the x-axis, quantization is basically taking points from the y-axis, right? Yeah. So basically, we are like while analog to digital conversions, we need discrete levels. Like we cannot take all the range from 0 to 1 inclusive. We have to take discrete levels. So these lines are there. Hence, the quantized signal after, like analog to digital converted. Like this is just one example for demonstration. If we talk about unit impulse, at origin unit impulse, shifted unit impulse, a sine wave and an exponential signal. If we talk about sine wave, then this is how we created sine wave, and over which we did sampling for both sine as well as exponential. Like you can see the stem plots. We are moving towards sampling here. Okay. Moving on to convolution, which sir did today also. Like if this is a input signal, which is a rect, which we call rect, and we are convolving with a triangular wave, we are getting this. You can see, right? Again, if you are convolving a triangle with a triangle, we get a structure like this. Both of these are important as for smoothing of signals. We require different type of say, output signals to get convolved with, right? Like I will show you how. Like if this was the input signal, blue one, after convolution with a rectangular triangular one, we are getting this convolved output. Same, more complex, like what I did here. I had a signal which was sine, which I added with the noise, right? And the noisy signal is this basic, the blue one, convolving with the signal which we created above. See, you can see a much smoothened signal. This is a practical demonstration where students can see the practical use of convolution. Like people generally don't get why we convolve. This is why, to get a smoothened signal, right? With the noise signal, जो smoothen आपने कुछ नहीं समझा मैं. इस signal के साथ हमने convolve किया है यहाँ पे. Yeah. So my input signal was this noise डाल के, and I convolved with this one. Yep. हाँ. With a window size of 5, right? हाँ. Like again, we impulse response. If you are doing convolution, like sampling wise, we are getting this convolved, right? Talking about Fourier transforms, like this only was discussed yesterday. Like this is a signal containing multiple frequencies. As you can see, if you are taking part like f1, f2, and f3, in the frequency domain, you can see f1 frequency is showing this peak, f2 this, and f3 this, right? Like these are theory, but not as of your use, but okay. Signal reconstruction, which we did today, Nyquist, and this, like Yep. Sine wave f max is 20 and fs is 30. So what will get? Right? Yeah. But this is for you. You can take. You can tweak around. Yeah. Right. That's so. What was we doing? Like we are sine wave for 20 hertz, but sampling is at 35, which is less than which is less than up to 2 times 20. So these are points we got after sampling the stem plot and the linear reconstruction. So this is how this is not creating it properly well. The reconstructed sine wave doesn't match with this. The stem plot. So basically, what we did, if this is the this is the x-axis. We are drawing the stem plot like to create this point. Okay. Again, like if you are sampling for greater than the 2 times max, then we are getting near equal. Like real case scenario, we need even more. Like this is nearing to this. Still, it is missing. As you can see, it is not getting the points properly yet. Like twice the maximum frequency. In that case, now it's getting nearer. Like this is the difference between the theoretical and the practical aspect of sampling. I hope you all getting. Yeah. Like there is a difference between theoretical and practical aspect, right? For a frequency just greater than 2 times f max, it was giving a hint like it can match the original signal. But for mood, yeah, it is trying to replicate. Still, there are sharp points. And this was for the DTFT. So to skip करो उसको मैं. Like basically what I am trying to say यहाँ पे like this is an original signal. We will ignore this. Okay, this is a signal which is basically constituent of two signals of 440 and 880 hertz plus noise, which were discussed in the doubt. In the Fourier domain, we get two peaks of 440 and 880. Rest are the noise. Hence, we can use if you know filters, we can use bandpass filters to get this. And same sampling and reconstruction of two sine waves. Like again, with the same sampling, like if f max is 20, I'm using sampling frequency of 100, which is more than twice, to get around a replica of this. Okay, and this is for the Fourier approximation, like how many terms in the Fourier series can help us replicate this rect one. Like if this is the original fx, then how many terms would we need to get a replica of this? And all of this are coded here. I've put comments so that it will be easier to understand. Okay. Okay. So there is another Gibbs phenomena which also help us to realize the magnitude and phase of the whole transform. Like it is the same thing which we did here, but we were analyzing for 5 terms, 10 terms, 15 terms, and 20 terms. That is for more than 50 terms. Like as you can see, it is going for 101 terms. That's why we are getting near that box thing. Okay, and it is just if you know the Bode plot and all, we are just here analyzing if this is a time domain signal. As you can see, this is not a regular signal but consisting of many frequency. We are trying to get its magnitude spectrum and the phase spectrum. Why it is necessary? To get the stability and right. But again, this is more used in I would say controls. But yeah. Okay, I hope this was clear. But okay, I tried to rush it through, but this was clear. But okay, I have made enough comments and the language in between so that it would be clear if you do it offline, right? So I will shift to another project. This was a Python one. So now I will use GNU Radio, which is a type of software which is used in SDR. SDR is basically software defined radios. Why it is used? To basically simulate hardware radios. You can use SDR to replicate FM modulation, AM modulation, and any other signal processing pipelines. Why I'm using this? Because GNU Radio is an open source software, helps you to graphically analyze the signal processing pipeline throughout. You can do basic input output, time domain analysis, frequency domain analysis, filtering also. I will show you. I have 8 sub assignments which I will demonstrate you now. But I just need my file up here. GNU is a platform and radio for software defined radio. I don't remember. Like
GNU's full form is actually very interesting. GNU stands for, the G stands for GNU, the N stands for not, and U stands for Unix. So it's actually a recursive abbreviation. GNU is GNU not Unix, which is GNU not Unix not Unix.
okay. So this was the document which I used 2 years ago as a part of my department festival, electrical department festival Impulse. So I will share this document with you also. Like it has all the installation packages like for Windows, Linux, and Mac. Right. We'll just start with the introduction to GNU Radio. As I said, is a free tool that helps you work with radio signals on your computer, like a full toolbox handling different radio signals, just like MATLAB, like Sir was saying, Octave or MATLAB. This document has all the basics, which I will just skip through. Like how do you start a file? How do you add blocks? What is the throttle? We need throttle because we need to limit the CPU processing power. Like there is a catch in this while making flow charts. If you don't add throttle in the whole pipeline, then it will utilize the whole of the CPU power, right? And they are visualizing signals like time sync and frequency sync, which you'll see just now. Like this is how it looks, right? Slide controller, and this is how you connect blocks. Like I was saying, it's a graphical flowchart manner, and this is how you execute. And I've created a whole tutorial just for your demonstration. You can see it later, like a step by step how to create a flowchart, how to start, how to set up, what is the signal source, what is the throttle, what is a time sync, frequency, how to connect blocks, and how to run the flow graph, and including the basic blocks like what is a low pass filter, how you can use to make it a high pass filter also by just changing the cutoff frequency and the window method, VCO, rational resampler. Rational resampler is to use to change the sampling frequency in between. So I will just move ahead. Like this is for you only. आप यहाँ पर पढ़ सकते हो कि हर एक ब्लॉक का क्या यूज है. And I will just skip to the end. Like what's next? Like you can. There is a website also which helps you create your own FM radio. You sir बोलते हैं RTLSJ होता है. This is a very small hardware which is available in labs, which you can use to receive signal from the environment and play it on your computer. Like we had one of this in our communication lab. Okay. So I will start with the demo one. As you can see, I have set the sample rate. These are the blocks, right, which I was talking about. I have set the sampling rate at 64,000, right? The first signal is a cosine wave with 2000 as frequency, and the second signal as sine wave with 1000 as frequency. So this won't cause any aliasing as such. What I'm doing, I'm adding, right? Let's show you how, right? As you can see, I'm adding these. This is basically cos 2 omega t plus sine omega t, adding to get a time sync and uska frequency analysis. Also, it's individual time analysis, right? What I'll do, I'll just play. Sine, double frequency cos, adding will give me this, and iska frequency analysis. You can see two frequency here. This is a clean signal, तो मेरे को बहुत cleanly दिख रहा है इसके two peaks. This is the origin, positive, negative, right? Let's go to multiply. मैंने multiply के लिए बहुत एक basic से use किया है, which is sine theta. Theta is basically a frequency of 1000 hertz, cos theta and 2. So 2 sine theta and cos theta. Output will be sine 2 theta, right? Sine and the product. Yes. Right. Next, I will let you know about the sample rate which we are discussing. Right. Uh, right now we are sampling at 160K. Right. As you can see, it is smooth enough. Phase shift around, like this is a multiplier which is helping us to showcase, like you can see that time axis is changing. But let's say if I change the sample rate, it was 1K, right? If I change the sample rate to by 32, 1K, I'm tuning the sample rate to check out the signals, the software defined signals, right? Let's say I do by 32 by 10. You can see distorted, like we were seeing the Python assignment. This is a practical way of seeing ki how changing the sample rate beyond अपने signal source का sample rate can affect the whole signal. Yeah, we are. So basically, it connects to the hardware, right? So hardware adds as an advantage. Yep. Uh, hmm, yeah. And the hardware radio, right? Uh, yo. SDR sir means software defined radio for any software here, right? For radio, yeah, we can manipulate them. Like if we are trying to receive through a radio antenna, and we are trying to transmit it through this as a black box, we can manipulate that.
This we did by Starcom software. They had a software. So they were showing all this kind of things.
Those are paid software. Like this is the open source software, a much miniaturized version. Right.
I will show you after that.
Sure, sir.
For all this.
Yep.
This is more interesting for students.
Yes, that's what I was trying to say.
If we show this software, this thing, because it's having application domain communication.
मेरे पास अभी जो बाकी फाइल है वो ज़्यादा इंटरेस्टिंग ये तो बेसिकली आर द ट्यूटोरियल्स विच वी शो इन द फर्स्ट 2 लेक्चर्स टू हैव अ प्रैक्टिकल एग्जांपल की ऐड कर दिया मल्टीप्लाई कर दिया सैंपल रेट चेंज कर दिया लाइक देयर इज समथिंग कॉल्ड rational sample. So rational sample is a block which adjusts the sample rate, like the interpolation decimation. Like if our sample rate is 32,000, so interpolation multiplies the sample rate by 5 and decimation divides it by 7. We use this in FIR and IR filter. Yes. Yeah. Right. Like yeah. This is the original and this is the resampled one. And उसका frequency analysis इसका ही and इसका ये. Yeah. ये frequency increase नहीं हुई sir. आपने उसको resample किया तो उसका sampling चीज हो गया तो aliasing हो गया. So it is like अभी what we thought कि theoretically it should be greater than 2, right? But practically we're seeing that around 10 times or 20 times it was copying that whole manner. कि frequency से चेंज नहीं किया ना, the frequency सेम कहा गया 1K, resample कर दिया इसको 5 by 7 times. Like as you can see, मैंने यहाँ पे क्या आ रहा है? Sample rate as no sample rate 32K 32K. So yeah. Yeah, नहीं 5 by 7. ये देखो सैंपल रेट क्या हो गया आपका? सैंपल रेट इंटरपोलेशन बाय डेसिमेशन, इंटरपोलेशन बाय डेसिमेशन डाउन कर दिया. यस राइट. अरे हाँ फिर
ओरिजिनल जो सिग्नल है आप रीसैंपलिंग में 5/7 से मल्टीप्लाई उसकी कीमत तो कम होनी चाहिए.
सर वो आपकी ये आपकी फंडामेंटल फ्रीक्वेंसी तो रहेगी सर वो फ्रीक्वेंसी कम नहीं हुई वहाँ पे, उसका ये इसका ये चेंज हो गया है, लाइक उसका ड्यूरेशन सैम्पलिंग आप चेंज कर दिए तो उसका द पॉइंट्स.
ये बस टाइम स्केल इसका डिफरेंट है.
यस
फ्रीक्वेंसी सेम है, सेम ही सिग्नल है ऊपर.
हाँ जी.
टाइम स्केल थोड़ा ले लें आसपास देखते हैं.
यप
ज्यादा से ज्यादा नहीं लगा तो सिग्नल सेम रहना चाहिए. कोई सिग्नल में सैंपल किया.
Okay, so next is upper frequency domain analysis for a real time audio. I would like to say, okay, like I've used a single type of frequency as a chirp video, chirp audio form. आवाज आ रहा होगा पूरा, लाइक उसका टाइम पे ओके टाइम एक्सेस में ऐसा है वेव फॉर्म एंड सेम इन द फ्रीक्वेंसी. यू कैन ऑब्जर्व कि उसका फ्रीक्वेंसी बढ़ते है, श्रिल होते आ रहा है. नहीं अगर मैं इसके आगे देखो ऐसे बढ़ते आएगा. हाँ जी. Next, I have filtering example where we are using band pass filter. I have used a song which was popular back in 2 years. I don't know how many of you are aware of this. हाँ हाँ देख कल इन लोगों ने वो बोला कि भैया गाना चेंज कर दो, गाना को ढंग का. अभी मफल्ड है. अब मैं क्या करूंगा क्योंकि मेरा हायर ऑफ द कट ऑफ फ्रीक्वेंसी कम है, मैंने बढ़ा दिया. क्लियर हो गया. अब मैं लो कट ऑफ फ्रीक्वेंसी घटा दूंगा टू अवॉइड नॉइज. मेरा वोकल चला गया. हाँ और मेरा अभी मेरा ट्रांजिशन वीडियो छोटा रखा है ना, ट्रांजिशन वीडियो बड़ा रखा दूंगा. आपने जो उस टाइम देखा था, वेट, जब हम लोग इसको कन्वॉल्व कर रहे थे विद दिस, तो देयर वाज ऐसा द ट्रांजिशन विड्थ, सो वी आर मैनिपुलेटिंग विद दैट. अब मैं इसको थोड़ा कम करता हूँ. ऑडियो ऑडिबल हो गया. तो वोकल्स नॉइज अभी भी है. So manipulating with the low cutoff frequency, high cutoff frequency, we can get a noise free signal. हाँ जी इसमें बहुत फ्रीक्वेंसी, अभी कितना नॉइज है इसमें एकदम ही क्लियर नहीं है. मेरे को उसको बहुत टाइम तो उसको ठीक करना पड़ेगा विद ट्रांजिशन विद का मल्टीपल पॉसिबिलिटीज विद लो कट ऑफ हाई कट ऑफ टू गेट अ प्रॉपर नॉइज फ्री सिग्नल. किन दोनों को ट्रांजिशन जीरो तो खत्म हो जाएगा सर. ओके अभी थोड़े पहले जीरो ही था. अब एक और मेरे पास, ये इसमें ज्यादा मजा आएगा क्योंकि इसमें बस मैं उसमें बैंड पास यूज कर रहा हूँ, इसमें मैं लो पास यूज कर रहा हूँ. ये रेडियो से है, ये रेडियो से है. ये माइक का है इसका. आवाज आया राइट सबको. अब मैं इसमें क्या करूँगा, इसलिए कट ऑफ फ्रीक्वेंसी को चेंज कर रहा हूँ. आवाज आना बंद हो गया, लेकिन जो वोकल्स का फ्रीक्वेंसी उससे नीचे चला गया, खत्म हो गया, बस नॉइज बचा. हम्म हम्म तो टॉप जो उसमें जो पीक कर रहा है दैट इज बेसिकली द वोकल्स, बाकी वो नॉइज है, मतलब कि दिस ऑडियो इज एक्सट्रैक्टेड फ्रॉम द रियल टाइम ये रेडियो, तो उसमें जो नॉइज आता है लाइक इफ यू आर ट्यूनिंग टू एनी एफएम लेट्स से 97.5 तो उसमें नॉइज भी आता है, तो उसका नॉइज को लोग देख रहे थे उसको फ्रीक्वेंसी कैसे, बिकॉज जिसमें जो वोकल्स होगा उसका ऑफ कोर्स उसका फ्रीक्वेंसी ज्यादा रहेगा, बल्कि उसका हिस्टोग्राम पे बिन्स ज्यादा रहेगा, ऊपर रहेगा, सॉरी बिन्स बोलो क्या बोलते हैं उसको, एनर्जी ज्यादा रहेगा, राइट, हाँ एनर्जी ज्यादा रहेगा, सो इन दैट वे वी कैन कट ऑफ, लाइक आप इसको ऑब्जर्व कर सकते हैं इस अराउंड 8000 हर्ट्ज, यहाँ पे आ रहा है। मैं क्या करता हूँ एक बार दिखाता हूँ मैं इसको, और जो हम ये देख रहे हैं बेसिकली रिफिल्टर्ड है, वो सर वो तो एक अच्छा खासा 1 घंटा एक्सरसाइज है वो, हाँ ये आपका रियल टाइम सिग्नल है और फिर उस पर फिल्टरिंग करके ये आ रहा है आउटपुट, दिस इज द इनपुट, दिस इज द आउटपुट, हाँ जी कम कर दिया और फोकस होगा बीच में, ये तो सर है ही नहीं ना, इसका आपका पीक ही जा रहा है आपका 0.13 किलोहर्ट्ज, ये आपका है क्या अभी शो नहीं हो रहा है, लाइक सर यहाँ से देख सकते हो जैसे कि इसका अराउंड जो कट ऑफ है वो 1.08 किलोहर्ट्ज पे है, वो वोकल नहीं सर 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 माय बैड आई गेस सर कंफ्यूज, वो वोकल फ्रीक्वेंसी नहीं, दैट आपका जो बेसिकली जो मेजॉरिटी ऑफ द नॉइज है, सॉरी जो मेजॉरिटी ऑफ द वोकल है वो इस पे लाइक कर रहा है, तभी हम लोग इसको ले रहे हैं, ये आपका कुछ परसिस्टेंट नॉइज है जिसको हम लोग हटाने ट्राई कर रहे हैं इन द एक्सरसाइज, माय बैड वहाँ पे, हाँ जी यस वर्ड की मल्टीपल नॉइज, हाँ हम वही बोल रहे कि हम लोग वोकल्स को एक्सट्रैक्ट करने ट्राई कर रहे हैं, मैं वही बोल रहा कि हाँ क्या वो एक बहुत बेसिक सा ऐसी मस्ती है, बेसिकली व्हाट वी हैव डिड यहाँ पे वी क्रिएटेड वेक्टर सोर्स विद द होल आपका सी, हैप्पी बर्थडे में आपका डिफरेंट कॉर्ड्स है, सी कॉर्ड डी कॉर्ड ई कॉर्ड, तो दिस वाज एन असाइनमेंट इन आवर लैब, मैंने उसको कॉपी पेस्ट किया, लाइक यू कैन सी द वेक्टर 26 26 26 26, so basically it is trying to replicate that particular frequency for particular amount of time, दिखाता हूँ नहीं मैं शेयर करूंगा, एंड आई yeah, मैं इसको कम कर दूंगा तो फास्ट अप हो जाएगा, क्योंकि मैंने ड्यूरेशन ही कम कर दिया, लास्ट एक इक्वलाइजेशन था, बेसिकली अगर एक ऑडियो फाइल है जिसमें मल्टीपल फ्रीक्वेंसीज है, डू यू नो हाउ इक्वलाइजर वर्क, मैं अगर सबका फ्रीक्वेंसी बैंड में आगे पीछे करता रहूंगा, लेट्स से कि इसमें मल्टीपल बैंड्स है, मैं अगर दिखाऊं मल्टीपल बैंड लाइक इन द सेंस ऑफ ऐसे 9 to 15 6 to 9 3 to 6 500 to 3 22, so you're hearing basically the noise or audio pattern between 6 to 15 kHz, yep, so yep, this is from my side, from the simulation side, I hope you liked all of this, like both the Python part and the GNU part. मैं कहीं rush किया, I'm sorry, थोड़ा सा मैं बीच में lag किया, but this was the first time I was demonstrating the whole of thing. Yeah, if you have any doubts, you can reach out to me, WhatsApp पे कर सकते हैं, इसमें discussion तो कर लूँगा मैं, and I will share all of these files with you on WhatsApp. Yeah.